Welcome to the Mechatronics Revolution Fundamentals and Core Concepts. In this lesson, we'll talk more about microcontrollers, microprocessors, and embedded computers. The objectives of this lesson are to, number one, identify the core elements of a microcontroller, explain the difference between microcontrollers, microprocessors, and embedded computers, and then identify the types of applications where microcontrollers are used. As you can see, microcontrollers come in all shapes and sizes, and there's a lot of different variety in their capabilities. So as we decide which microcontroller to use for our particular application, it's important to understand how they work, and then what are the key elements, and how they compare against devices like embedded computers or microprocessors. A microcontroller is a miniaturized computer containing a processor core, memory, and input-output peripherals in a single integrated circuit. Unlike microprocessors, which are designed for computers, microcontrollers are designed for embedded applications. Sometimes we'll see a microcontroller unit abbreviated with the letters MCU. And throughout this course, we'll use that abbreviation quite often. When we talk about embedded applications, it's important to understand what we mean. Embedded applications are some type of device or machine that uses a computer in order to do some calculations and give some commands to things like actuators or sensors. Some examples of embedded applications include a dishwasher, a thermostat, a camera, microwave. Even a lot of children's toys would be considered an embedded application that use microcontrollers. Embedded applications are fundamentally different from computers because computers are not designed to do some other function besides computation. And so, for that reason, computers use microprocessors and not microcontrollers. Comparing microcontrollers and microprocessors a little closer, one of the key characteristics that makes microcontrollers different from microprocessors are the input-output peripherals that microcontrollers have on board. These might include devices for communication with other microcontrollers, or devices to convert analog signals to digital signals, or digital logic pins that allow microcontrollers to send commands to an actuator or receive binary information. Microcontrollers have much slower clock rates than microprocessors do. Typically, for microcontrollers, we'll see clock rates in the megahertz range versus microprocessors, we'll see clock rates in the gigahertz range. Microcontrollers also have a much smaller memory space than microprocessors. Typically, on microcontrollers, we'll see memory spaces in the kilobytes range versus very large memory spaces for modern microprocessors in the gigabytes range. One thing you'll notice when buying a microcontroller is that it's a lot cheaper than buying a microprocessor. Microcontrollers are typically in the tens of dollars range or even cheaper than that, versus microprocessors are usually a lot more expensive in the hundreds of dollars per unit. In addition, microcontrollers don't really run an operating system in the same way that microprocessors might run a Windows operating system or a Linux operating system. Microcontrollers will only really run the program that you supply to it. Finally, one of the other key characteristics of microcontrollers compared to microprocessors is that they use a lot less power. That's really important for a lot of embedded devices because a lot of embedded devices run on batteries. Another type of computing technology that we see a lot more often are embedded computers. Microcontrollers are different from embedded computers. You might have heard of some typical embedded computers like the Raspberry Pi or the Odroid, which are used in a lot of robotics applications. Embedded computers are a type of middle ground between a microcontroller and a microprocessor. Embedded computers have some of the same type of input-output peripherals we might see on a microcontroller, like digital output pins or serial communication devices, but they have a lot faster processor than a microcontroller will, and they have a lot more memory. And in that way, they're a lot more like a microprocessor. Embedded computers are designed for real-time applications, just like microcontrollers, except we use embedded computers when we need a lot more advanced processing or advanced software. An example of something like that is computer vision. If we build a robot or a mechatronic device that needs some type of computer vision system, that software will not usually run on a microcontroller given very limited memory. As a result, embedded computers run an operating system that's similar in nature to what you might find on an actual computer or a microprocessor. Finally, as a result, embedded computers are usually more expensive than microcontrollers, in the $50 range or $100 range, depending on the model you buy. Sometimes we'll hear embedded computers being referred to as single board computers. It's important to understand the elements of a microcontroller. Microcontroller is composed of three main elements: a central processing unit, a set of input-output peripherals, and memory. And each of these three main elements are combined on a single chip and connected through some type of data bus that allows these elements to pass information back and forth. Starting with the central processing unit, or the CPU, the CPU serves to execute program instructions. There's three main elements to a CPU. First, the control unit, which is typically some type of clock, and that generates the timing signal that's used to get a program instruction from memory and execute it. Secondly, there's the arithmetic and logic unit, or the ALU, and that performs the actual instruction on one or more pieces of data, for instance, adding two numbers. A final element of the CPU are the registers. Registers are memory locations that are inside the CPU, very close to the arithmetic and logic unit, that hold that internal data that's being processed. Microcontrollers have two different types of memory. They have volatile and non-volatile memory. Volatile memory is memory where data is maintained only as long as power is applied. If we remove power from volatile memory, then data will be lost. Unlike volatile memory, non-volatile memory maintains our data even when power is removed from it. There's a lot of different types of memory on board microcontrollers, and this table shows a lot of detail about each of those different memory types that you might find. But the most important are EEPROM or flash memory and static RAM or SRAM. These are the two most common types of memory spaces you'll see on a microcontroller. Flash memory is a type of non-volatile memory where our program is usually stored and where we can write data that we want to maintain even when power is removed from the device. Static RAM or SRAM is a type of volatile memory, and that's where our program usually stores data, but that data is lost every time power is removed. Another key element of a microcontroller are the general purpose input-output pins, or GPIO pins, that allow us to interface the microcontroller with other devices like a motor or a servo or a sensor. We'll discuss GPIO pins in a lot more depth in the upcoming lessons. So to summarize, microcontrollers are small computers and they're specifically designed for embedded applications. They're different from microprocessors because, number one, they include onboard input-output peripherals. In addition, they usually have less memory and are a lot lower cost and lower power devices. The main elements of a microcontroller include a CPU, memory, and input-output peripherals. And embedded computers have similar processing and memory capabilities as microprocessors, but like microcontrollers, they also include these input-output peripherals.